Hi, this is Dr. Andrew Chrysler teaching communication systems. In this set of videos, I'm going to be talking about ideal versus practical filters and how practical filters can be realized and why ideal filters are not possible to build in real life. If you're not in my class, you might want to follow along by checking out this book by Lathy and Ding, as this is the text I use for reference. So, talking about ideal filters, which we did in the previous set of videos, we came to the understanding that ideal filters would have no distortion, which means not only will they have no amplitude distortion, but they will also have no time delay distortion, which is a separate piece of information. Right? So this means that all pass filters may still contain some time delay distortion. In further terms, right, we spoke about this lack of distortion, meaning that the amplitude response is going to be constant. So we didn't say that this has to be 1, but it does need to be some constant value. And you also need to have no time delay distortion, meaning that you had a constant slope angle on your phase response. And for all of this, right, you would do this at least over the frequency band that you require to be filtered. So taking a look at the first filter that we considered, an ideal low pass filter, this is what the amplitude and phase response would look like. Again, we can take a peek at this and see that yes, the amplitude response is 1. That's a constant over this band of interest. So from minus B to B. And also we can see that the phase response is a line, it's linear, and it has a slope of minus TD. So this meets our no distortion criteria. So the filter doesn't change amplitude over this bandwidth B of interest, and that bandwidth B would be some frequency in which you're using. And then also all of the components in B, so all of the phase components in this have the same slope. There's no point in time when this slope changes to some different slope. And again, if that happened, right, this would look like if all of a sudden, if we had a linear from here, and then for some reason the slope changed or was steeper in some points or the other, right? That would constitute a change in the slope angle, which would be equivalent to some distortion. Now, this same set of criteria could also be applied to a high pass filter. And this should say high pass. So in the ideal high pass filter, you would also have the same situation where your filter does not add any amplitude distortion. It's constant over your band of interest, and also you have a constant slope of your phase angle. This would be the same for a band pass filter as well, where you have 2 different bands of interest centered around a frequency of interest. Over your band of interest that you're allowing to pass, there's no amplitude change. And then over the entire set of frequency, you have a constant slope, a constant time delay. So therefore, all components that pass through this, regardless of the frequency, have the same time delay.